Good afternoon, everyone. We are Team Fall 2, and today we're presenting our project, the low-cost EMG-controlled 3D printed prosthetic hand. Our sponsor is Duvian Rojas, and our faculty advisor is Dr. Garawardi. Our team consists of Shirel, Elise, and myself, Anya. Our goal for this project was to design a functional, affordable prosthetic hand that uses EMG activation that helps transrail amputees to be more independent. So the upper limb loss affects 3 million people worldwide and about 540,000 in the US. Most are working age adults and 57% are transrail amputees. However, 50 to 60% users stop using their prosthetics. As shown in the pie chart, amendment is driven by discomfort, poor fit, weight, and difficulty controlling the device. This gap is what motivates our project. Clinically, users need something that's lightweight, comfortable, mechanically reliable, and easy to control. Many commercial options are heavy or complex. Research prosthetics are cheap but not durable. The result is high abandonment, especially in early rehabilitation. Commercial myoelectric prosthetics cost between $20,000 to $100,000, and insurance rarely covers the full amount. Repairs every few years and add to the long-term burden. Meanwhile, the 3D printed hands online are not FDA approved and can be used for adult daily activities. So there is no low-cost, clinically usable functional prosthetic today. So this table shows the major differences. Research prosthetics are low cost but break easily and lack real functionality, and market prosthetics are functional but extremely expensive. This contrast validated the need for a middle ground solution like ours. The current modalities, so body-powered devices are durable but uncomfortable. Myoelectric hands are functional but expensive, and 3D printed research hands are customizable but not durable. Our device is lightweight, low cost, and functional enough for basic grasping. Now Elise is gonna talk more about our objective of this project.
Thank you, Anya. Right now, I'm gonna talk about our project scope and project objective. Our project objective is to produce a myoelectric hand with low cost, having an EMG control, having a basic grip around 5 to 10 newtons. We're gonna have a internal string routing, and it will be PLA printed hand. So this is our our design table with the market requirements, design inputs, and important standards. Our market requirements means that our device needs to be affordable, needs to be easy to control, lightweight, safe to wear, must be securely holding daily objects, and must be skin safe. So for our selection of our MVP was developed by the criteria of cost, complexity, sensors, manufacturability, weight, reliability, and timeline fit. So for the three concepts, the first concept was the one that it was the lowest cost, lowest complexity, has the lowest sensors, and it was the easiest to manufacture. So these are the two subsystems that we have. Basically the whole hand assembly and the subsystem of our electrical components, where we have the two motor sensors powered by the Arduino and the battery, where we're gonna be control using a myoware sensor to control to capture electrical signals from our body. We did some simulations to talk about it. The first one is a static simulation where we developed the stress, displacement, strain, and the factor of safety. The stress showed a higher, it showed a low stress on the fingers. It is more on the rods. However, there is no stress where it's gonna show this deformability. The displacement, there must have there must have a, what is the name of that? I'm so sorry, guys. I'm so nervous. It must have an error during the simulation where it happens where in the point of the fingers. However, it's still a place where there's not gonna have a deformability during the simulation. The strain shows the same thing, and the factor of safety shows that if we use less than 68 newtons, that it was the force that we applied on the fingers, it would the simulation would fail. The drop test shows that we wouldn't have much deformability on our our simulation. So even if we drop, it would be fine with all of the stress and strain, so we wouldn't have a deformability on the socket. And the thermal strength shows that we have a higher temperature in the middle of the socket. However, this is basically due to the concentration of heat of our electrical components. Now I'm going to pass to Shirel to talk more about manufacturer accessibility.
For manufacturing and assembly, all parts. For manufacturing and assembly, all parts were printed in PLA using FDM printing. Assembly involved mounting the servos, motors, threading the internal fishing line tendons, integrating wiring, and securing the socket. Our total cost, including material, labor, and overhead, was estimated to be $639. For our verification plan, we developed six verification tests: the grip force, non-slip grasp, EMG response, thermal safety, comfort and material safety, and environmental performance. This test checks that the device met the design inputs. For our verification results, all our tests are currently in progress. The grip force must reach at least 5 newtons. The EMG activation must reach at least 80%, and the surface temperature must stay below 40 degrees Celsius. These tests will finalize as assembly and tests wrap up. For our verification summary, this table summarizes all our verifications and all acceptance criteria. Every category is in progress, but as of now is meeting our expected values. For our intellectual property, our device includes several potential patentable features. Single sensors, EMG controlled, internal steering routed, modular 3D printing construction, and socket with integrated electronics. These features differ from previously patented EMG systems. For our athlete feedback, our user interview guided was several design decisions, prioritizing functionality over aesthetics, simplifying control, reducing weight, and creating a simple strap-based socket. This is direct feedback from this direct feedback help us make our designs better and adaptable to real user needs. For our accomplishment, by the end of Serial 2, we achieved a low-cost EMG control and a lightweight design until under 1 kilogram with a functional grip strength, safe operations, and full modularity. Everything is reprintable and it's easy to maintain. For our future work, it includes multiple grip patterns, proportional EMG controlled, a full wrist movement, improved socket comfort, durability enhancements, and a formal user testing. We want to acknowledge all our faculty from FIU. We want to thank Dr. Garavardi, Professor Shahristani, Dr. Christie, our alumni mentor Sofia Mendez, our sponsor Duvian Rojas, and some students that help us in the designing and troubleshooting of our device. Here is our references, the appendix, and thank you everyone for your patience. We are happy to answer any questions.